In this video, we are going to introduce the concept of equilibrium using some simple conceptual examples. So here is an example of what we might call an equilibrium. So let's say, for example, we have an acid-base reaction where we have 5 molecules of green acid. I'm going to go ahead and put some hydrogens on all of our acid molecules so we can remember that that's the proton donor. Okay, and 5 molecules of base. So we've got our total of molecules over here on the left-hand side. Please remember that we never have only 5 or 10 molecules of anything. We have many, 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 many molecules at play all the time. We're just simplifying to a few molecules to understand this conceptually for now. So let's say every molecule of base, I'm going to put a lone pair on this base and draw an acid-base mechanism. Every molecule of base reacted to form the conjugate base and conjugate acid. So we know that conjugate acid now has the proton. I'll draw it in green. Every molecule of our conjugate acid has that proton. Let's say every time that base found an acid, it made a conjugate base, conjugate acid. So we would have all of these pairs reacting. That would give us all of these pairs of conjugate acid, conjugate base on the other side, if everything perfectly reacted. This can happen with strong acids and bases. Every molecule of acid finds a molecule of base and becomes conjugate base and conjugate acid. We don't have any starting material or original acid or original base left. That can happen. But sometimes we do have a little bit of leftover. So here in this example, we have our same 5 molecules of acid, same 5 molecules of base. But what do we observe over on the right-hand side? When I look, I see, okay, I still have a molecule of acid and a molecule of base left. I mean, a lot of it converted to become conjugate base and conjugate acid, but we still have a little bit of that starting material left, or our acid. But most of it reacted to form products. Okay? When this happens, we call this product favored. At equilibrium, and we'll define what equilibrium means in just a second. At equilibrium, we have mostly products formed and just a little bit of our reactants left. This is the case when the conjugate base and conjugate acid together are more stable than the reactant side. So the reason we have so much conjugate base and conjugate acid forming and staying formed is because they're more stable in this case. You can imagine when we start using real molecules, you'll be able to use what you know about stability to predict, is the conjugate base, conjugate acid the stronger or the weaker, the more stable, the less stable. Okay, so in this example, when we have a product favored equilibria, the conjugate base and conjugate acid are more stable compared to the other side, the acid and base side. But here's the reverse trend. So we still have our same 5 molecules of acid, our same 5 molecules of base. If the base and acid are the more stable compounds in this reaction, we would see most of our starting material is still sticking around at equilibrium, and we only have a very little amount of product formed. We call this reactant favored. When we at equilibrium have more reactants left over, because they're more stable, the acid and base are more stable, the reactants are more stable, we call that reactant favored. We only have a little bit of product formed. Okay? So here's a third scenario that's maybe not quite as obvious as the other two were. So I'm going to circle what I have in my right-hand box. I have what appears to be 3 molecules of base, 3 molecules of acid, 2 molecules of conjugate acid, and 2 molecules of conjugate base. Just looking at that picture, we would say, if this was at equilibrium, we would say there's more reactant left over than product. The concentration of reactant is higher than the concentration of the products. Therefore, that is reactant favored. We can see there's more reactant swimming around. But how do we know if something is at equilibrium or not, right? We can only claim something to be reactant favored or product favored when we're at equilibrium. Well, what does that mean? Is it a time? Is it a what is equilibrium? Equilibrium is defined as when the concentration of products and reactants stops changing. Okay, so when the concentration of our products and reactants stops changing, we say we're at equilibrium. Here's an example of what that might look like. So if you start a reaction, an acid-base reaction in the morning, and then you walk away and you come back at noon, and you test the concentration, you measure the concentration of your acid, your base, conjugate acid, and you record what those are. And then you leave and you go away, come back a few hours later, and you take those measurements again. And you see that the measurements are exactly the same. Over time, that concentration of your acid, your base, and your conjugate acid, conjugate base hasn't changed, all right? The concentrations are now stable. They're the same. So we would say that that reaction is at equilibrium. And we could take a look and see, okay, do we have more reactants or do we have more products? And we would be able to assign whether the reaction was reactant favored or product favored because we're at equilibrium. The concentration of products and reactants isn't changing. However, just because the concentration of those things isn't changing doesn't mean the reaction stops. And this is a really confusing concept. So we would, like I said, we measure the concentration at noon, we come back a few hours later, we measure the concentrations again, we see the concentrations are the same. One might assume that the reactions have stopped. No more mechanistic arrows are forming, no more bonds are breaking and forming. That's actually not true. The reaction is still going on, it's reacting in one direction at the same rate as it's reacting in the other direction. So here's a picture of that. For example, we say one molecule of A reacts with a molecule of B, and we know that forms conjugate base and conjugate acid. Cool. At that same rate, just as often, at the same rate, conjugate base is reacting with conjugate acid to form our reactants and products again. So we're going backwards. We're doing the reverse reaction. When those rates of forward and backward are the same, that's when we've achieved equilibrium. That's when the reaction is at equilibrium. And that's still happening. A is still reacting with B to form conjugate base, conjugate acid. Conjugate base is still reacting with conjugate acid to form acid and base back. But as long as those rates of reaction for forward and backward are the same, we're at equilibrium, and the overall concentrations that we can measure will not change. This is important because many acid-base reactions are reversible, and it's important to note that a reaction is never stopped reacting. All right, there's always a dynamic equilibrium of this forward and backward process happening in reverse for most acid-base reactions. So here on this last slide, I want to reiterate what we actually mean by the definition of equilibrium. So when the forward reaction and the reverse reaction are happening at the same rate, we call that a state of equilibrium. Another way to say that is that the concentrations of reactants and products are no longer changing. That means the same thing. We have a constant or a small equation to calculate basically a number for an equilibrium, and that equilibrium is very specific to each reaction you do. So the equilibrium constant K tells us how product is formed relative to specific reactants at equilibrium. So we always have reactants on our left-hand side and products on our right-hand side. And when we set up our equation for K is just a constant. We put the concentration of products over reactants. Well, on our other slide, we could map that to say, okay, we remember acid was in green, the concentration of acid versus the concentration of base. We'd measure that and put that in the denominator. The concentration of our conjugate acid, I think our conjugate acid was purple, and our conjugate base was green, or yellow, excuse me, it was yellow. So we measure those concentrations and we can put that one over the other and we would get a K value, okay? If K is really large, meaning products, there's many more products than reactants, we call that product favored. If your K value you calculate is small or less than 1, it's a decimal or a fraction, we would say that it is reactant favored because your denominator would be really large. If K is equal to 1 or very close to 1, we would say the concentrations are very similar to each other, okay? And so we're going to look and use this relationship for K, whether it's large or small, to predict whether something is reactant favored or product favored. It also has implications for that thing we've been using called pKa. We use K to understand pKa, but we'll discuss that more in another class.